I've never seen a duck with such luscious locks.
They say I'm a rare breed.
At the end of the beak is so disturbing.
Yeah, it's really scary. I kind of love it though.
That's so good. That's so good. Oh man, that puts my potato to shame. Or what was I? The pineapple in this mess or the potato? That's so good. Okay, I'll try not to be too distracted. Hi everybody. So welcome back to episode 1 million of Pandemic Algebra. So let's see some announcements. First announcement. Actually, maybe this is just a question, a request for sort of nominations. So I just got an email saying that for commencement this year, well, I didn't want to share anything. Stop. Okay, this is not okay. I'll just do this and then stop sharing it. For commencement this year, they want to do some success stories. They want to do some like personal interest stories on graduating students who have a sort of a nice story about them. And you guys are awesome. And every student has overcome unbelievable odds to even get through any courses here. But you guys are getting through some really freaking tough courses on your way to graduating. And so if you know of, like, if you might think to yourself, Justin's had to suffer with that. I mean, Justin, I just call you Justin again. Oh my God, Jordan's had to suffer with that like tremendous beak, and he still managed to do well in class. Or if you want to nominate somebody, I'd love it if you send me their names, and I'll forward it to the people who want to do these pieces. And it'd be nice to honor you. I would love to honor everybody in the class. Even those who aren't graduating, but maybe we'll honor it by just getting through and surviving till the end. Hope that happens. Okay, so that's announcement 1. Announcement 2 is that, hey, last day before spring break. So one of the true, and I'm not kidding at all, one of the great joys of my week is seeing you guys here. This is such a good class. You're so fun, you're so smart, you're so alert. And yet I'm looking forward to not seeing any faces in any boxes for like at least a week, right? It's gonna be great. So, glad to see you and glad to see you go. And then we'll see you when I get back. We'll all be refreshed and ready to take on the last 5 weeks or whatever there is left. I hope 4 weeks, something like that. Another thing I should say is that a lot of you, does anyone else have any like comments or stories they want to tell before I start angling myself into today's subject matter?
I got a new windshield today. That was kind of a big deal. I got a new windshield.
A new windshield, okay. So you didn't want to just replace the cracks. You were just like, that's too good. I'm too good for that.
It was like kaleidoscope style. Like the whole thing was just a million pieces, and it was like 4 months like that. So it was time.
Anyone else? Yeah, I don't have anything good to report. Oh, I'm gonna do something. I think I'm gonna try to do something really fun and over break. Well, fun if you thought the painting stuff that I showed you was fun, it's along that lines. But it's going to be funny. And I don't want to tell you yet because I'm hoping I do it and then I can show you and then you'll have more of like nerd effect. But I got something in mind that I think is going to be good. But that's all I'm doing over break. I'm going to just I'm going to stay off the computer. I'm going to try to sleep, maybe, see what it's like outside and, try to have a life. Remember what I used to do when I had a life, like try to remember that and do some of that. See if I still like it. Who knows if I even like it anymore, right? Okay. Jail. I'm missing out on all the. That's just so good. Okay, so and then there was the survey, and that was really, really useful. I thought it would be really useful, but I was wrong. It's way more useful. I read through it, and there's some incredibly thoughtful, reflective comments. And I realized that between last night and today, I didn't have enough time to process them completely. Like, I really do want to think about all of them and then also try to sort them and see like which ones are like common themes, and then which ones should I address separately, and which so on. And I haven't had a chance to do that yet. So I will do that over break, and I'll talk about the themes and if there's any like adjustments that I can make based on suggestions and that sort of thing. We'll talk about that when we get back. But two things that I want to say. One thing is that one compound thing is that several of you expressed how challenging it is to be a student during these times and how much Zoom sucks. And yeah, man, I hear you. And it's so hard to focus, especially on something so hard, you know, whenever there's all this other stuff going on and life feels surreal. You know, I hear you. I'm not able to help, or if I could, I don't know how yet, but whether I can help or not, I just want you to know that I hear it and I appreciate it. On a related note, it also sucks for your professors. Like we got into this because we like you and we want to see you in person, and this is and we kind of feed off of the energy, right? And this is not as fun, and it's a lot more work, sort of tracking people down. And but you wrote really kind things, and that was really touching for me, and it was really uplifting, you know, to be able to read these things and to feel like, okay, this effort is being seen and appreciated. And I just want to thank you for that. That was really encouraging and nice, really nice to read. So thanks for that. That's going to help get me through. And then the other one comment that I don't remember somebody in which group made, but I'd already been thinking about, had to do with the new point system. And, you know, this was the first time I've ever done it. And of course, it's, you know, it's going to have flaws. And one major challenge is that I don't even really know what my feeling for what should be an A is, right? Like, I've never done this before. So I like, for my other classes, I'm like, I can just give an exam and I know kind of what level of proofwriting feels like an A to me, but I don't really have a sense for this. So I made something up, and then somebody pointed out, well, you know, what if I get all E's, but I missed one too many homework assignments? Then I can't get an A anyways. And I'm like, that doesn't really make sense. So I'm working on some kind of like trickle down point economics system. I'm not quite sure what it's going to be, you know, but, you know, the Gipper is here to help. I don't know if you don't know me well enough, I'm not a trickle down economics fan, but I think the statement's funny. So, okay. So I'll see if there can be like Hopponomics. Okay, that's right. I'll see if we can do something like, you know, let's suppose you have one too many E's, but you have a P that you really wish was an S. Maybe I'll let you like take some of these points and you know, bump one of them up, you know, take something down and move it around, or I'll come up with some sort of creative point moving around situation. I haven't thought through it enough, so I don't know what it is, but there will be one trickle down point system, Hopponomics, coming soon to a algebra class near you. So I remember there, so when I was a high school student, I was a punk rocker, and why am I telling you all this? So this is in the Reagan era, and I had this friend who could draw really well, and he would like draw pictures of Reagan with a magic marker on my mirror on the wall, and then we'd like shoot it with Windex, and all the red would smear. And it's like, yeah, Reagan. And there was a song about Reaganomics, this punk rock song by, I think it was DRI. It's like 25 seconds long, and it just says, Reaganomics is killing me, Reaganomics is killing you. And I don't know, so that word just makes me laugh. Okay, so that's my distraction for today. Does anyone want to say anything before we do some math? let's get to some math. Okay, so let me pull up the chat window. Maybe you're already saying stuff and I just can't see it. Hold on. Okay, there it is. All right, so last time, where were we? I'm just going to scroll up and show you. You don't have to write anything down. You have it in your notes. I just want to remind you, I didn't remind the previous class, and then everybody felt kind of lost. So, you know, their loss is your gain. So last time, here's what we did. We had, you know, we had this group. We picked Z6 and addition mod 6, and a subgroup, which was just 0 and 3. And we figured out what were, these are left cosets. We figured out all the left cosets. And then we realized if we took the multiplication table and we rearranged it so that we put the elements of a coset, all those elements next to each other, and then elements of a different coset next to each other, then we got this sort of block multiplication structure. Where if we just sort of blur our eyes and think, you know, this is one element, the blue element and the red element, then we get a group. So that's cool. And so that would be cool if that always happened. And so let's do some investigation. So what I'm going to do is I'm going to give 2 classwork problems, and then I'm going to put you into some breakout rooms to work on it. We'll probably spend like 20 or 25 minutes in breakout rooms because I really want you to be able to think about this. I'm going to give you 2 problems, and I want you to figure out the left and the right cosets, and also try to make that sort of group table like we just did with, you know, rearrange things according to the cosets and see whether you get that sort of group structure again. So here are some classwork problems. Okay, does it help for me to remind us what section we're in? We're in Cosets and LaGrange's theorem, so section 10. Okay, so classwork. Here's 2 different problems that I want you to do the same thing to. So one of them is the group is D3. That's the dihedral group with 3 elements. I don't know if I ever said that word D before, but that's what D stands for, dihedral. That just means it's the group of symmetries of an equilateral triangle. So G is D3 and H is just the set. There's the subgroup 0 and, oh my gosh, 0 is not anything. Row 0 and mu1. And the other option is G is the same thing, D3, and H is the subgroup row 0, row 1, row 2. So first of all, what were the rows and the mu's? Can somebody remind the class about what those components were, what those elements were?
Rotations and mirrors.
Yeah, rotations and mirror images. So the rows are for rotations and the mu's are for mirrors. And if you look at those and they don't look like R's to you, but they look like P's and you call them P's, then you'll forget that P stands for rotation. They're so those are rows, lowercase R's, lowercase Greek R's. So rows, and row 0 means, you know, don't rotate at all. Row 1 means rotate 1/3 of a turn. Row 2 means do it twice. And then there's no row 3 because if you do it 3 times, you get back to the identity. Okay, and mu1 is just a mirror reflection where, you know, whatever, you fix one of the vertices and then do the mirror reflection like that. Okay, so what I want you to do with these are threefold. So for each, find all the left cosets, find all the right cosets, and rearrange the multiplication table you don't have to do the way I did with like sort of cut and paste stuff. You can just rewrite the multiplication table. So just start fresh and group the coset elements together and just fill in off the original table and see to group cosets together. To see if we always get this cool group structure. on the cosets. Okay, and maybe you don't have this in front of you. So where is it? Hold on, I have it somewhere on my desktop, and I'm going to share it with you in a second. Hope I can find it. Oh gosh, where did it go? Oh, I've lost it. When you have it, you definitely, oh, here it is. Okay. Okay, let me put it in the chat. Okay, so I think I just sent you what the standard multiplication table. You don't have to think through these products every time. I don't mean that, just look it up in the table. I just want you to use the table to do these two exercises. So are there any questions about what the exercises are before I break you up? I didn't notice you cracked me up comment. That's funny. Before I break you up into your breakout rooms. We're good? Okay, here we go. Open all rooms.
Understand how we got 0, 1, and 2. I forgot. Maybe Dr. Hoppus can help.
I came by just in case somebody was stuck.
Good thing, because I'm stuck.
Okay.
So I'm looking back at the example we did in last class for finding our left cosets. And I remember that we did our 0 plus H, our 1 plus H, and our 2 plus H. And I understand why those are like left cosets, but what I'm confused on now is why is it 0, 1, and 2 plus H? I feel like it made sense when we were doing it. And now that I'm trying to go back, I'm like, where did we get those numbers from?
Well, what you really have to do is just choose. So you already know if you choose something that's in H and you multiply by elements of H, you're just going to get H back, right? So picking something in H is not going to give you a new coset. So H is one of them. Let's not do that. Pick something that's not in H, then you get a coset for it. And if that's everything, then you're done. And if it's not, pick something else that's not in the things you've already seen. So it doesn't really matter. We did 0, 1, and 2 were convenient because I knew once we got to 3, we would wrap back around to 0.
Right.
But I could have picked 0, 4, and 5 or something like that if I wanted to.
Okay. Okay. And then, sorry. Actually, no. I think if I work it out, then maybe I'll be able to answer my own question. I want to see if I can answer my own question. It's okay.
You can try to answer your question. Does anyone else have something before I go to the next group? No. Okay. Let's see. Hey, just stopping in to see if anyone has any questions.
I don't know if we know what questions we have yet.
Yeah, have you just not thought about it yet, or are you just so confused you don't even know how to start? Or
okay, I'm just gonna be honest. Like, I was like the past 2 classes I've been a little lost, just on like my side. But I'm working through it. We're doing it.
Doing it, okay. All right, so well, let me help you get started. Okay, so if you're going to get the cosets, so let's do the first one where we've got row 0 and mu1. That's H. So we're going to take left cosets. So what we're going to do is take, we're going to take H, and then we're going to pick another element, and then have it be on the left when we multiply by elements of H. So whatever our element is 8 times H1, whatever our element is times H2, we're going to make another set out of that.
Okay, and that other element is G?
Well, G isn't an element, it's a whole group. So
Okay.
you would pick something in there. If you pick something in H already, see, if I have a subgroup H and I pick an element H out of it and I multiply by everybody, since H is closed, I just get H back. I don't get anything new.
Okay.
So I've already got H as one of the cosets. Now let's pick something outside of H.
Okay.
How about row 1? So do row 1 times first element of H, row 1 times second element of H. And that will be another coset. And if that's everything, then you're done. And if it's not, go find another element that you haven't already used up.
Okay.
Oh,
I was just wanted to ask, like, I thought the definition for a coset was like if the A inverse times B was an H. Like,
That's a definition of when they're equivalent, when 2 things would be in the same coset.
oh, okay.
But the definition of the coset A capital H was all the A little h's, where little h was in capital H. So A capital H is the set of all the A little h's.
Okay.
Is this going to help you get started now? Do you have questions, more questions about it?
no,
I think we're good for now.
I think that makes sense.
Okay, call me back in if there's no shame in being confused. I'm like, here's what professors do. They deal with confused students. That's our job, right? You don't know something and then we try to explain it and then later you know it. So if you're confused, like I'm used to that, just call me.
I embrace it, really.
Embrace it, yeah. We'll move on. Okay, I'll be around and just call me in if you have a question.
All right.
Will do. Thank you.
For each element of D3.
I think that when we're doing the left one, we have the element of D3 on the left, but like each individual element of D3 gets starred with H, and I think that's its own coset. Like we would do row 0 star H, which would be, hold on, I need to look at that would just be like row 0 star row 0 and then row 0 star mu1, which is just row 0 and then row or mu1. Oh yeah, because that's the identity. I think that's it because
Hi, I just thought I'd check in and see if you're doing okay getting started or if there's something I could do to help.
We're just looking at D3.
Okay.
I think there's 8 elements, but I've only found 6 of them, so I'm trying to figure out the last 2.
Oh, I gave you the multiplication table for D3 in the chat.
Oh. I must not have seen it. I must have like gone to the breakout room too soon.
Yeah, I didn't see it either.
Do you still have access to it or no? I can,
I'm looking at the chat and I still have access to it, but I can't see the document.
you can't, it's just a picture. You can't download it if you click on it.
No, it doesn't say that you've like sent a message at all.
Yeah, I didn't see a message either.
Okay, let me see if it's gonna send it to everyone. Let's see if this works.
Oh, there you go.
I got it.
Yeah, sorry, I didn't mean to make you do all that work over. I was hoping you just use something that you already had.
All right, thank you.
No problem.
Do you know what you're, do you know where you're going from here? Because some other students felt a little bit lost about next steps.
I'm not sure.
So to find the left cosets, you're gonna, so you're gonna start with your H, and then you're gonna pick an element of the big group. And left cosets, whatever that element is, you're gonna go, that element times element of H, that element times element of H, element times element of H. You're just gonna take whatever one you just picked out of D3 and multiply it by all the elements of H. And it's on the left, elements of H are on the right, the thing you picked on the left. And that's gonna give you a different set, okay? That's one of the cosets. Now do that again. Until you see what all the different cosets are for it.
Okay, thank you.
the set of, hello, Dr. Hoppus.
Hi, just seeing if everyone's okay.
I have a random question. Are we supposed to like name these cosets, or do we just like leave them as the little elements that they are?
Yeah, they're named row 1 times H.
Okay.
Yeah.
Okay. Can we ask if we're on the right track?
Sure. What do you got?
We have only done our left ones so far, and we did 4 of them because we got 4 elements that weren't in H, and they ended up being the same. Like 2 of them ended up being the same as each other, and the other 2 ended up being the same as each other. So there's 2, I think.
You only have 2. You have 2 cosets that besides H.
Yes. H
Yeah. Okay.
itself.
Okay, that makes
Okay.
sense. Mhm.
Okay.
Yeah,
We're
so far,
good.
Okay. All right, I'll give you a little more time. You still haven't done the multiplication table part?
No.
No, I didn't. I know I asked it. That's I'm super judgy, but I just meant I'm trying to judge what's a good time to call you back. Not, yeah.
We were like
That's just
explaining
different
it to
snacks,
each other.
right? So I'm okay.
Yeah. Okay. So
Matter whether you looked at the rows first or the columns first, right? When you're looking at the table, if you looked at the row 0 on the,
You don't know it's an abelian thing. So like for left, you do like, for example, for the left coset, you do like P1 on the row times something on the column, because your P1 is going to be the wait, I guess we did right coset first, then didn't we?
no, we still did left coset first, I think.
Because left coset is A.
And then row 1 with mu3.
Yeah, I guess that makes sense because the set H is row 1, mu1.
Thank you. Everybody's, are you doing okay?
Yeah, we're a little confused, or at least I'm a little confused because I'm just kind of looking at the example we did last class.
Mhm.
We did, or I don't know, I'm just confused because for the left coset specifically, there's like certain elements are in 2 different well, they are the same coset because they have the same elements, but like it just appears twice, and like I don't know.
Yeah, so
We
it's really just one coset. With the
Okay.
one coset containing those 2 elements.
Okay.
It has 2 different names. Maybe that's the way to think about it.
Okay. And then also, do we have to do 2, because the left cosets are different than the right cosets, and like the example we did last class, it was commutative, so that's why it didn't matter. So does that mean we need to have 2 different tables?
That's a good question. Let's just do one table. Let's just do the table for the left cosets, but that's a really good observation, and that's going to play into the answer to the bigger question.
Okay.
Just do left ones for now. Hi, just stop it in.
Hello.
How's it going?
Hello.
That's good. I think we got for mu1 that it's a left coset. It gives us back what we want.
Or you can have mu1 can be part of a left coset or a right. It will be part of a left coset or a right coset.
Okay.
So are you meaning something different?
Possibly. I think I'm
Do you want to try to ask a question?
I don't know the question yet, but I'll work on it and get back to you.
Okay, no pressure. I'll be around. Ha! I've been talking this whole time and the mute was on. Here's my cat. So okay, so what did I say? Oh my God, I said all these things. Well, one thing I said is you can always tell when the breakout rooms are going well when you call people back and they don't even notice because they're so busy working. So nice job on that. Good to see you back. And I just thought now would be a good time to come back because I think everyone's made enough progress that you kind of know where this is going. So let's just check in to make sure that we all did the same thing. So for this first classwork, I worked it out myself, and there's our group H. Let me move this out of the way. This thing's annoying. There's a subgroup H, and we take the left cosets. Well, we take row 0 on the left. Well, anything you take out of H, you just get H back. H is a group. Multiply by an element of H, you're going to get the group back. That's not a surprise. Then I picked another element, and I got, multiply on the left by that element, and I got this. Another element, multiply on the left, and I got this. Why did I stop here? Why didn't I use mu1 or mu2?
Because they would give back our H.
Yeah, mu1 would give back H. Mu2 would give me the same, it turns out would give me the same coset as this one. So, once I had all the elements of G represented, I had all the cosets. I didn't need to go find any more. So they would have different names like this coset right here would also be named, since it would also be named mu3H. And if you go look up, because mu3 times row 0 is clearly mu3, but the other one will also work too. So it's got more than one name, but it doesn't matter. We just need to know what the cosets are. These are the cosets. And those are the left cosets, and then these are the right cosets. So did anybody get anything different from this that you want to ask about? No. Okay. So when we did you have a chance to try to resort the multiplication table? That's the most.
I almost finished.
You almost finished? Okay. What happened? Well, maybe I'll give you just like 1 more minute. Everybody try to deal with the multiplication table for a second, and then we'll talk about it. I'm gonna get another chip. You can probably hear me chewing. Oh yeah, that's right. Okay, well, here's what it looks like when I did it. I started multiplying, and we shouldn't be surprised about this and this. Of course, this is going to work because row 0 is the identity. So of course, this is just going to stack up nicely in here. That's not a surprise. And then I just started multiplying some more. I was like, oh, hey, this one worked nicely. There's a block already. Maybe this is going to be good. And then I got here and I was like, oh crap. Because mu1 times row 1, mu1 times row 1 is mu2, and that is not red. So I couldn't make this block. This wasn't a block of red and it wasn't a block of green. It was just a nothing. So it didn't work. The whole group thing didn't work. The block group thing didn't work. Crap, it would have been fun if it always worked, but it didn't. Okay. Here's another example. Since H has 3 elements and G only has 6 elements, there's only going to be 2 cosets. There's the original H and then the other guy. So there's the left cosets, there's the right cosets. And it actually, you don't even have to color it. Some people, when they just looked at this, picture, I think back when we were talking about D3, somebody said, oh, wait, there's a sort of block diagonal thing going on. There's this sort of symmetry. You could just see like all the rows are here and all the mu's are over here. Like they segregate themselves. And, a 2-element group isn't that exciting, but in any case, this is a 2-element group. So, so it did work. So there was a block structure. There was a block structure here. And we did get a group. So here there is a group structure on the cosets. So if I think of a coset as a single element, then there's a group structure moving those single elements, which are cosets around. Okay, so sometimes it happens and sometimes it doesn't. And can anyone see, I gave you all the conditions, maybe you didn't know it, but I gave you all the conditions to be able to see when it's going to work and when it's not. Can you tell what's different about this classwork assignment than this classwork assignment?
Is it the 2 versus 3 elements in the coset?
Well, that has a little bit to do with it just because when I came down to a 2-element thing, that would have had to be a group, so when there were 3 elements in the coset, that meant that there were 2 different cosets, and that's just going to make a group. So kind of, but it's actually something more general than that. Can anyone see? Well, look what happens. Oh, you want to try it, Lori?
Sorry, did Lori say something?
Oh, I don't know who said something. Maybe it was, I'm sorry. I heard a noise and I thought it was Lori.
I was just going to say, is it just that there's, in the first example, we have two cosets that aren't H for left and right. And in the second one, we only have one other coset that's not H.
Well, I think that's related. Let's just stop chewing, sorry. I think that's related to your first comment where, when there's only one other coset that's not H, then it's going to be, you're right, it is going to break into a group structure, 2 elements. You already know the identity is going to work the way you think the identity is going to work. So that's going to be fine. But this region, I don't know.
Does it have to do with it being commutative?
Kind of, except that if you look at D3 isn't commutative either way.
Okay, yeah, I was just looking at it and I picked like 2 examples, and I guess the 2 I chose were.
Oh, okay. Yeah, okay. So here's what it is. So if I look at these cosets, and it's kind of dorky because there's so few of them. It would look much better if we had many more cosets, but then it would have taken us all day, right? So we have to pick our battles, but like this left coset is the same as this right coset. That's pretty cool. That's not a surprise because it's just H, but also this coset is the same as this coset. If we look up here, okay, this coset's the same as this coset. That's not a surprise, it's just H. But this red coset isn't anywhere down here. There's no row 1 mu 3. They're just different. The left cosets are different from the right cosets. Let's color I didn't need it. Here we go. Whereas here, the left cosets equal the right cosets. That's the difference. That's the difference. Okay, so here's the moral. If you have a group and a subgroup, if the left cosets are the same as the right cosets, then the operation on, oh, I didn't finish writing this, sorry. I must have distracted myself. Then the operation on G forms a group with the cosets. Okay, left cosets equals right cosets. That's the condition where it will work. There are some groups where the left cosets will always equal the right cosets, and I think we've already sort of hinted at that, but can somebody just fill in that thought?
Would it be groups that are abelian or commutative?
Yeah, that's right. Groups that are abelian, this will be true. The left cosets will always be the right cosets because it doesn't matter what order you multiply it in. So abelian groups will always have this cool structure on the cosets, but non-abelian groups can have it because D3 is not abelian, but it can have it, but it won't always have it. All right, so that's the moral of that. Are there any questions you want to ask about this very long example before we move forward to new things? Okay, this is all sort of leading up to LaGrange's theorem. Well, this is just the title of the section, so I'll make it this color. Okay, so here's something just to notice. Now that you've done some cosets, I hope this is just obvious to you. Every left coset or every right coset has the same number of elements as H. We found that. You just take H, you hit it on the left, you hit every element of H on the left by something, you get a new set. Of course, there's going to be the same number of elements as you have in H. Okay, so but that's a useful observation for this theorem. Here's the theorem. So okay, let H be a subgroup of a finite group G. In that case, then the order of H divides the order of G. Okay, that's the LaGrange's theorem. And I'm going to draw the picture that, I don't know if I ever actually saw this picture or if I just made this picture up in my mind when I was learning it. And then now I just see this picture every time I think about it. But here's the way I like to think about it. So we've got this group G. And then there's a subgroup H. So here's H. Some of the elements, not all of them, let's just say. Then we're going to take some left cosets. So if I choose some element A and I take the left coset AH, as long as A isn't in H, I'm going to get another set. And that other set in G has the same size as H. I can do that again. I take this B and I'm gonna get a BH. And then, you know, I'll probably have like a CH and a DH. And let's say, I won't say E because it look like it didn't, but an FH. And then each of those has the same number of elements as H. And all the elements in G get used up, right? Because if they don't, then you pick another element that isn't seen in any coset yet, and you make another coset out of it. You know, you can stop when every element of G is in one of the cosets. Okay, so in my mind, I've got things split up like this, and here's H, you know, H is the main guy, and these are all the cosets of H. Okay, so here's what the proof looks like. Proof is almost more complicated to write down than to just know. So let's just give these things names. Let the order of G be N and the order of H be M. Well, so H has M elements, so every coset of H has M elements. Every coset of H has M elements. Okay, how many cosets are there? Well, let's say there's R. So if R is the number of cosets, let's see, this is a partition. Every element of G is somewhere. Every element of G is on only one of those boxes. There's R boxes. Each box has M elements in them. Okay, so that means, since that's true, then R times M is N. The number of boxes times number of elements in each box is the total number of things that you have. In other words, M divides. Okay, so it's just as obvious as maybe it feels intuitively.
Would you need to specify anywhere that like the cosets don't have any overlapping elements?
So yeah, that is super important. And did we prove that at some point earlier? I don't remember. That'd be a good, if we didn't, that would be a good exercise to practice. It's not very hard. It's probably like 2 lines or 3 lines, but the thing that would be hard about it is sort of understanding what there is to do, but it's, but once you do that, then you can just follow your nose to it. So maybe this is an interesting exercise to practice. So show that that 2 cosets are either disjoint or the same. So show that 2 cosets are either disjoint or the same. In other words, show that if X is in AH and X is in BH, then AH is BH. I guess we did something like this with orbits, didn't we? But maybe we didn't. Oh, this is crazy. But maybe we didn't do it for cosets, but it's true. And so this would be a good thing to try. But you're right, we do need this. And it's also a true statement. So we have it. And the LaGrange's theorem follows from that. What other questions does anyone have? You know, Lagrange, triggered some people last time, but this is kind of a cute little theorem. Maybe he's like, maybe you're warming up to him a little bit now. Like maybe it's not so bad. Okay, here's a corollary. Oh, actually, I wanted to tell you, I've got a bunch of algebra books. And I like to read all, well, sections of all of them before I teach, just so I can have a bunch of different perspectives to be thinking of things from and that sort of thing. And I was looking at one of the books, and the authors, after this, the author said, never underestimate the power of a theorem about counting. And I thought about that and I was like, yeah, okay. And then he said it again. And he's like, it's so important. Later on, he's like, had it in bold. Never underestimate the power of a theorem that involves counting. This may seem like a dippy little problem, like, oh, okay, there's that many of these, this many of these, this time this is that. But you can prove some powerful things with it. So here's two things that you can prove with it right off the top, right off the bat. So here's one of them, which, you know, I think is surprising. Well, now that I know how the proof is, it's not surprising, but it should have been surprising before I knew what the proof was. So every group of prime order is cyclic. Everyone's cyclic. This may be less surprising to you because we haven't spent a lot of time talking about groups that aren't cyclic. But like D3 is an example of a group that's not cyclic. The Klein 4 group isn't cyclic. D3 has 6 elements. Klein 4 group has 4 elements. Those aren't primes. You might think, well, we've never seen a finite group that's not cyclic of prime order. Of course, because there aren't any. Okay, so maybe this isn't as surprising to you as I think it should be, but anyways, yeah. So there's nothing weird. The only thing you get is a cyclic group of that order. And here's how the proof goes. The proof uses Lagrange. Okay, let's suppose G is a group of prime order. So let G be a group of order P, where P is a prime. How could we prove that G was cyclic? How do you prove a group is cyclic? Does anybody remember what cyclic means? Just brain fuse, everything's gone.
Isn't it where you have to find the generator where like every element is of the form like A to the N where N is in Z?
Yeah, that's exactly right. So we're going to try to find a generator. So the way we could prove it's cyclic is we could show that we can find a generator and that everything in the group is just some power of that generator. Yeah, okay, so that's what we're trying to do. What could a generator be? Well, let's just think of it this way. Let's just choose an element out of G. If we accidentally chose the identity, well, that wouldn't be a generator, right? Because the identity, all powers of the identity is just the identity. You don't get anywhere else. So that's not a good candidate. Let's pick an element that isn't the identity. Okay, so let's choose an arbitrary A in G where A is not the identity. And let's just think about, you know, since I have a finite group, I can, well, it doesn't even matter if I have a finite group, I can take the cyclic subgroup generated by A, and it's going to be finite since G is finite. Okay, so, and consider the cyclic subgroup generated by A. How many elements does that have? Since A isn't the identity, then the number of elements in this thing is more than 1. How many elements does it have? Think about Lagrange. What do you think? Is everybody just lost by
Is it-
now? No. I'm ready, Sean. Let's hear it.
Well, it's like I want to say n, but like that's not even like a, a thing.
Okay, we call it n. Okay, so if n is the number of elements, see, this thing right here is a subgroup. What does Lagrange say about subgroups? The order of the subgroup.
It says that the order of the subgroups divides the order of G.
Yeah, that's right. So the order of this group right here is going to divide the order of G. It's going to divide P.
So it has to be P.
It has to be P. That's right. So by Lagrange, the order of this cyclic subgroup divides P. Since P is prime, and that order is greater than 1, then the order is going to be P. Okay, there's P elements in that cyclic subgroup of G that has P elements. So they're the same. In other words, G is cyclic. And we kind of proved something a little bit more, which was, and every single element of G, that's not the identity, every single non-identity element of G is a generator, can be used as a generator. I just picked a random one and it works. Okay. Okay, so that's pretty cool. Here's another corollary. The order of an element in a finite group divides the order of the group. Well, what's the order of an element? That's the smallest power that you can take that element to before you get back to the identity. But it's also, we proved earlier, it's also the number of elements in the cyclic subgroup generated by the element, which divides the order of the group. So there's not very much to say here. Maybe I'll say it, I guess. The order of an element of a finite group is the same as the order of the cyclic subgroup generated by that element. Which divides the order of the group by Lagrange. I could name the group and name the whatever and so on, but this corollary is, the proof's so short, it's just like sort of 1.5 steps. I thought I would just talk through it. All right, so does anyone have questions about this part? by index. Here's a definition. So suppose H is a subgroup of G. Then the number of left cosets of H in G, it's called the index. And you write it this way. So if G is finite, how does this work? If G is finite, what's the index? So I'm going to go back. Let's just think about this picture. The index is the number of cosets. If I know how many elements G has and how many elements are in H, how many cosets do I get? Well, I just take number of elements in G and divide by number of elements in H. That tells me how many piles I have. So that's what I'm about to write. If G is finite, then the index of H in G is just the number of elements in G divided by the number of elements in H. If G is infinite, then we still have an index, but we can't use this formula because what does it mean? The number of elements in G would be infinite, and you can't divide that by something. That's just crazy. But we can still do it, and we did at the beginning of class last time. So we started with, we had the integers, that's an infinite set, and then we had the multiples of 3 was our subgroup, that's also an infinite set. We found 3 cosets. So the index of H in G is 3, even though both sets are infinite. Okay, here's kind of a cool theorem, and then to wrap up this section. I don't know a good slogan for this theorem, so I won't have a slogan. Suppose, oops, come back. Suppose you have this, like H is a subgroup of G, but you also have a subgroup called K. And suppose that all relevant indices are finite. So suppose the index of H in G and the index of K in H are both finite. Before I go on with the result of this theorem, I'm just going to draw a picture of what's going on. Here's what it looks like in my mind. So here's all of G, and then I've got these, then I've got H over here, and then there's a bunch of cosets. Here's a bunch of cosets. So the index of H in G in this case is 1, 2, 3, is 5. But then H itself has its own little subgroup, these yellow guys. So here's H's subgroup right here called K. And maybe H has, maybe there's 4 cosets for, let's just say, here's, I don't know, ZK, YK, and XK. And you can't really see H anymore, so let me. H is this coset. Well, this decomposition of H, that can be pulled around to decompositions. You can get yellow decompositions of all the other cosets the same way. So that's going to lead to, this kind of thing. Oh, oops. That's going to lead to this kind of thing. Etc. Does that make sense? It's going to pull them through all of these cosets. Okay, so what does the statement of this theorem say? The statement says, if the index of G and H, in other words, if the number of green cosets is finite, and the index of K in H, in other words, the number of yellow cosets in H is also finite, then the number of yellow cosets in all of G, if I took K as a subgroup of G, is also finite. Here, no. And well, how do I get the index of K and G? How many yellow sets are there? The answer is, well, it's the number of yellow sets. Oh, oops. It's the number of yellow sets in K. Sorry, number of yellow sets, cosets of K and H, the number of yellow sets here times the number of green sets we have. So it's the number of yellow sets times the number of green sets. We're not going to prove it, but I hope by the picture, I hope it seems at least believable. And believable is going to be good enough. Okay, I was going to do a little bit in section 11, but I don't think we really have time this time. So we won't, but I'm just going to foreshadow a little bit. So here's what mathematicians always do. They, you go into a new realm and you just want to categorize, what are all the groups? You might have even been thinking about this yourself, these, integers mod n, the symmetric groups, alternating groups, the dihedral groups, Klein 4 group, the integers with addition, the reals with addition, like the unit circle. What all is there? I mean, people just keep making them up, or can we categorize them? Can we classify? Well, there's these kinds and there's those kinds and there's those kinds. So classification is a big deal. And in fact, there's this incredibly powerful theorem about a subset of the groups, about finitely generated groups, finitely generated abelian groups. In fact, it's called the fundamental theorem of finitely generated abelian groups. And that tells you exactly what you have. If you have a finitely generated abelian group, it looks like this. That's all you get. Okay. But the suspense will kill you because we're not going to talk about it next time. But you've got some homework to work on. Turn it in tomorrow. Have a week and a half almost not thinking about algebra if you want, or catching up if you want, depending on where you are. And I hope everyone has a really great break, gets a lot of sleep, and comes back ready to go. I look forward to seeing you. Bye. Take care.
Thank you so much.
Thank you.
Thank you, Professor.
Thank you.
Thanks.